now we will talk about diffusion. So one of the reasons that we talk about diffusion is because, let's cut to the chase, d by dt of some quantity q equals some d, this is a number, this is a diffusion coefficient, times del squared q. This is the diffusion equation, or the heat equation. I'm going to derive this and show you where it comes from and talk about it. But one of the nice things about this is we can completely characterize the solution space. And we know that given any initial condition, we know exactly how this is going to evolve. And that's in stark contrast to Navier-Stokes equation, which has a term that looks just like this. There's just this other term in here, this nonlinear term that makes things hard, that makes things problematic, and makes it so that we don't have a complete understanding of the solution space. So you can, it is not known whether or not all initial conditions to the Navier-Stokes stay well behaved. If you can find some flow that makes the Navier-Stokes equation give you an infinite velocity, then that'll be an enormous accomplishment. But we have this diffusion equation, which we have completely characterized. So let's talk about it and let's characterize it. So the first thing we're going to talk about is random walks. We'll talk about it in 1D, and I mean all the cartoons I'm going to do are in 1D, and then we'll wave hands to generalize. So this is one of those things that I've done in various classes, like statistical mechanics. Nobody's taken StatMech, right? You've taken StatMech. Are you the only person in the class who's taken StatMech, or is there somebody else? Okay, thanks. So anyway, so you'll see this when you do StatMech, and you'll see it again when you do StatMech in grad school, because it's a pretty common thing. So okay, I have points in space that will number 1, 2, 3, 4, 5. Right. So these are now positions. I'm going to start at one of them. We'll call this I. And I can randomly move from this one to the next one with some probability p. And randomly move, I'm going to make this, so I'm going off of some lecture notes that I stole from somebody else online. And this is the way they did it. I'm going to post those notes because I think they're good. He did it with a asymmetric diffusion. So the probability to go one way is p. The probability to go the other way is q. So there might be some kind of net force directing us. So the question is, what's the probability that I'm this far away after some amount of time? So what is the probability? Now, I'm going to try to separate my little p and my little q. So big P, we want the probability that we've gone a distance m after n time steps. Does that make sense? So we're marching along in space. How far have I gone away from the center in n time steps? So what's the probability that I've gone m steps in n time steps? Well, this is just the same as asking what the probability is that I've taken n1 steps to the left and n2 steps to the right. So n1 is the number of steps I've taken to the left, n2 is the number of steps that I've taken to the right. And this is just going to be equal to little p to the n1 times little q to the n2 times the number of ways to do each one of those things. Number, hashtag doesn't make any sense. Number does. Pound does. Little g, let's stick with the notation that we like. N1, N2. So where little g is the number of ways that I can have N1 and N2. That make sense? Yeah.
Do different particles have like a bias to go one direction over the other?
Sometimes, if I have an electric field and they're charged, then there's going to be a bias to go in one direction. If things are rolling downhill but still bouncing off each other, there'll be a bias in one direction. So what is little g? Let us count. So I'm going to start here. There's one way for me to start there. Then my next step, I can either go here. There's one way for me to go here, or I could go here. There's one way for me to go there. Make sense? So now from this point, I can either go here or I can go here. So I can go here. There's one way for me to go here. If I go here, there's two ways for me to go here. I can either come from this side or from this side. One way to get here. If I take one more step, there's one way to get way over here. There's three ways to get here. There's three ways to get here. There's one way to get way over here. If I take one more step, then there's one way to get here, 4 ways to get here, 6 ways to get here, 4 ways to get here, 1 way to get here. This is called Pascal's triangle. And it's very useful for a bunch of reasons. So there's a number of things that make this a useful triangle. But you can just keep writing this down. And the order that I take the steps in doesn't matter. So if I'm going n steps, there are n factorial ways that I can order those steps. But we don't know which, so there are n factorial possible combinations, but we don't know which direction we went in, so, or what order we went in, so we have to divide by the degeneracy. So n factorial is the number of places that I could go. n1 factorial and n2 factorial are the different number of ways that I could get there. So let's try a different different mnemonic to get at this. I get here and I realize that I wasn't explaining this good enough. So let's do that better. So let's say I've got 2 buckets. I've got red beads in one bucket. And I got 2 beads. Actually, let's... Planning ahead. Planning ahead is so good. And when I've planned ahead the various explanations, then they come out smooth. And when I realize that I forgot one, and I didn't plan it ahead. Okay, I got numbers. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right? How many ways can I arrange these numbers?
There will be permutations, so just
yeah.
N factorial.
So it's just going to be n factorial. So how does that work? So I've got the first bin. I can pick any one of these. I have n choices for my first point. For my second point, I have n minus 1 possible choices because I've used 1. For my third point, I have n minus 2. For my fourth point, I have n minus 3. So the total number of ways that I can sort this is n factorial. That makes sense? So n factorial is the number of ways that I can sort a line. Now if I have, say I've got 2 buckets, and I have red beads in the first bucket, and I have blue beads in the second bucket. If I'm going to pick n beads, there are n factorial, again, n factorial ways that I can pick n beads from both of these 2 things. So say I've got 1,000, or say I've got n beads in total, so there's 400 here, 400 here, n is 800. There are 800 factorial ways that I could grab some beads out of here and some beads out of here. But I can't tell the difference between the beads. So they could have come out in any order. So the total count, so the total number of options that I have is n factorial. So this is, let's call this A, and this is B, and then n is A plus B, the total number of B's. But I don't know how many of, I don't know what order these are in, so I have to divide by all of the different permutations of these, so that's going to be A factorial. And I don't know what order these are going to be in, so I have to divide by all the possible permutations of those, so that's going to be B factorial. So if I've got two populations of things, and I'm just going to pick a random bunch out of both of those things, and it's going to be random which ones I pick and random how they come out. The number of ways to do that is the total number factorial divided by the first one factorial divided by the second one factorial. Does that make sense? Yeah.
So if everything you're pulling out of is identical, then there's only one way that it can be pulled out, right?
No, A is different from B. But they all know who they are, but I don't. So if everything's identical and I'm only pulling out of one population, then I'm only going to get one answer. So if I only had one bin, then it's going to be n factorial over n factorial is just 1. Does that make sense?
Yeah.
But I've got 2, so it's n factorial over A factorial, B factorial. So this is how you pick n of 2 random things. So if I'm going to take n1 steps to the left and n2 steps to the right, this is the same thing. I'm going to take n total steps, but which order I do 1 and 2 doesn't matter, so I've got to divide by n1 factorial, n2 factorial. This thing shows up a lot. This describes this. This describes how you expand a quadratic. So if I have A plus B to the big N, then what is this if you expand this out? How many of you know how to do this programmatically? Go.
Oh, A to the N? Oh, you want it as a sum?
Yeah. Write it short. Don't write all the way out. Because it's, okay, so if I do it, it's A to the N plus B, A to the N minus 1, plus C, plus B to the squared, A to the N minus 2, plus B cubed, A to the N minus 3, blah, 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 to B to the N.
Yeah.
So that's how if I expand out this binomial, I get this whole list of crap. But some of those things are repeated. So you know how if it was just FOIL, then I would have A plus 2AB plus C, or plus B squared. A squared plus 2AB plus B squared. A squared plus 2AB plus B squared. If I had this cubed, then I'd have 4 terms. I'd have A cubed plus 3A squared B plus 3B squared A plus B cubed. And it comes from the same kind of counting. So there's a way that we write this down. A plus B to the N is the sum on A to the N. We're going to go from N equals 0 to big N, A to the N, B to the N minus N, big N minus N. And then we have to count. And this gets a special symbol. It's just big N choose little n. And that stands for this factorial crap. So parentheses with big N on top of little n. This is new notation that kind of only gets used this way. It's not a fraction. It is n choose, big N choose little n. This is what this notation means. Have you guys seen this anywhere before? Yeah.
I've seen it, but I never understood it.
Okay. So all it is big N factorial over little n factorial times big N minus little n factorial. Which is the same thing that I did here. I just wrote it as n1 and n2 instead of n and big N minus little n. Okay, so we need that. We'll come back to that. I'm actually going to write it up here because we're going to need it in a second. A plus B to the N equals the sum on little n equals 0 to big N. Big N choose little n. A to the little n. B to the big N minus little n. And it's symmetric, so I could write this. I could write these as the other So we'll need that in a second. Okay, so I erased all the stuff I needed. That's what I get. Let's go back to where we were before. So I want to know the probability that I have gone m steps, that I have gone m points after n steps. And this is going to be big N choose little n, p to the little n, q to the big N minus little n, where little n is the number of steps to the right. I wrote it as n1 before, but we'll just write it as little n right now. All right, so this is the probability that after this random walk, I've gone m steps, m points after n iterations of my random walk. So what we want to ask is, how many steps have I gone? What is the expectation value of little n? How many steps have I gone to the right? So we're going to ask about the expectation value of n. So let's hold out for a second. Let's talk about probability. Okay, so some of you have taken quantum. Some of you are taking quantum now. So you've all seen a little bit of probability. But let's talk for a second. So if I've got some probability distribution P of x, then the average of x is equal to the integral of x times P of x dx. So this is P and this is x. This is my probability distribution, which I drew as distinctly non-Gaussian. So this is the probability that I'm at some position x, wherever that happens to be. If I just multiply by x and ask how much each x shows up and then add, and then divide by the number, oh, we already did that. So when you find the average of some quantity q, it's the sum on q, you add them all up, and then you divide by the number that you had when you make the average. So we take care of that. We don't want to divide by the number. We don't want to have to count all the time. So we make it so that our probabilities are all normalized. So the integral of P of x dx equals 1. That way we don't have to divide by how many things we had. We just have the probability distribution. So the integral of P of x dx is 1. The integral of x times P of x dx is just the average of x. If I have any quantity that depends on x, and I want to know what the probable outcome of that is, then we call that the expectation value of f of x. And that's just equal to the integral of f of x, P of x dx. So the expectation value of a quantity is just that quantity times p, and then you integrate. You'll see this in quantum mechanics where p turns into the square of the wave function. What I often want is the average of x squared, which is just the integral of x squared f of x dx. I also sometimes want the variance. You are too small to use. The variance, which is the average of x minus average x squared. So this is the average of x squared. This is the average of x minus the mean squared. This is a more useful quantity in a lot of ways because it determines how far away from normal you are. If I square this inside sum, this is equal to the average of x squared minus the average of x squared.
Wouldn't that be the variance squared?
Sure. No. I'll just call it the variance. That's the standard deviation squared. Is this. So we'll need this in a second. So what is the expectation value for n? So this is, I have some random walk. What is the probability? What is the probable size of n? When you do this, this is just the sum on n times p of n and n. Which we wrote up here. Wrote this in a little annoying way. Okay, m and n and little n. I wrote m on this side and little n on this side. N is the number of steps to the right. And so the number of steps to the right plus the number of steps to the left is the number of steps that you've taken. The number of steps to the right equals the number of steps to the left, or is the distance total minus the number of steps to the right. Did I do that wrong? No, plus. So you can see that number of steps to the right is 1/2 times the total number of steps plus the distance you've gone, and the number of steps to the left is 1/2 times the total number of steps minus the distance you've gone. So we'll need these. We'll actually just need this one in a second. I don't need you there. You're in my way. So n and m are related, and little n is n1. I'm going to get sloppy. So if I just say n, I just mean the number of steps to the right. So what's the expectation value? So in this random process, what's the expectation value of n? That is, I've taken big N steps. What's the probability, or what's the distribution of going, or what's the expectation value of how many steps to the right I've taken? Does that make sense? So we just plug things in. So this becomes, oh, there's another thing that I need. Do I need it? Oh, let's actually generalize this a little bit. I'm going to need this in a second. So I can say that P times Q, U times P plus Q to the N, I'm just rewriting the binomial theorem, but in a slightly different way, is equal to the sum on little n, big N, choose little n, U to the N, P to the N, Q to the big N minus little n. So here I'm taking P plus Q to the N. I'm sticking on this extra U. This is another quantity that I'm pulling out of thin air. I'm magicking this. I'm just going to multiply by 1 in some elaborate way. That's what this is going to do. But this is just the binomial theorem. So I just have UP plus Q to the N is just the binomial distribution. So I've got U to the N, P to the N, Q to the big N minus little n. I'm going to need that in a second. Okay, so the expectation value of how far to the right I've gone is n times p. So this is equal to the sum on little n of big N, choose little n, of n, p to the n, q to the big N minus little n. Now I can just add u to the n here, and we'll just say that u equals 1. Here's magic. I'm just adding, I'm multiplying by 1 in a complicated way. So now, the reason is I have this n, and I want to get this n into my equation by taking a derivative of something, but because I got n upstairs and I need an n downstairs. So let's take a derivative of something and get that n downstairs. But we want to take a derivative of something that's not actually doing anything. So that's why we introduce this u to the n. Also, I know from the binomial theorem what this is going to look like. So I can just stick this on, and I have something that I know what it looks like, and I'll just take it off when I'm done. So that way I can rewrite so this is the derivative with respect to u of u to the n, p to the n, q to the big N minus little n. Okay, almost, times u. So when I differentiate this with respect to u, an n comes down, and I get an n minus 1. So I got to multiply by another n. But that's okay. This u is a 1. So I can do that. So then, this sum only depends on little n. The derivative factors out. This u factors out. So here I'm left with u times d by du of, and then I'm left with my binomial theorem, u, p plus q to the n. So I have this thing, and it's a gnarly sum. But there's an n in it. And that n comes from taking the expectation value. But I need to get it some way that makes sense, so we'll try to get it as a derivative. So we'll turn this stuff into something more complicated, take a derivative with respect to this, and I get my n. So now my expectation value for n is just u, which is some magic crap that I made up, times the derivative with respect to this magic crap, times up plus q to the n. And I can do this. I can take this derivative. This derivative is easy. I get an n comes down, and a p comes out, and everything else cancels, and I'm just left with n times p, because u is 1. Everything else goes to 1. Does that make sense? So the expectation value of the number of steps that I've taken is just equal to the number of steps to the right is just the number of steps times the probability that I took a step to the right. That makes sense. This is kind of a horrible math way to go about getting something that makes sense. How many steps to the right did I take? How many steps did I take in total times what was the probability of taking a step to the right? It's pretty straightforward. Okay, so that's only kind of a useful result. Let's write it over here because we'll come back to it. The expectation value of n is the total number of steps times the probability of going to the right. So now we want to get a probability, an expectation value of n squared. Why would I want that? Well, if I have some random point and I go this way, then 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 I go this way. If I'm really random, I'm just going to orbit this point. So the expectation value of the distance that you've gone is 0. Now, that's not what I did. I took the number of steps to the right. So the expectation value of the total distance you've gone, I'll do in a second. But that's going to be about 0. But that's not always the interesting quantity. So say I'm running around a track. Like, do any of you guys run for fun or for fitness? You ever go to a track and run around a track? What is your average velocity when you're running around that track? Burning lots of calories, sweating like crazy, your average velocity is 0. Even though it's really fucking hard to run and run and run and run in a circle. The average velocity, the average displacement is not what you want, yeah.
So when the average x is 0, that's assuming that the probabilities of going left and right are similar.
Yeah, that's true. That's exactly right. So, and I'll show you that. That's a really good point. We'll come to that in a second. The thing that I care about often is x squared, which is not 0. That's going to be big. So when you're running, if you're running around a track, the thing that you care about is not your average position, it's the square of your average position, because that's a big number. So this is 0 because you got some positives and some negatives. This is all positive. So we want the variance because it tells us about what the physical system is really experiencing. So we need the variance squared. We're going to go through this same process where we just write down what we want. We're going to add a square here. We're going to do the same stunt, but we're going to turn this into a second derivative. And what we're left with, I'm not going to bore you with the algebra. It's very straightforward. This just turns into a second derivative, and you get the second derivative of this, which is then equal to, if I could do it in my head, I would, n times p plus n minus 1 p squared. So n times p from when you take the first derivative, and then n plus p plus 1 is the second derivative. So we'll need this too. The expectation value of n squared is n times p plus n minus 1 times p squared. So now the question that we really care about is not how many steps I went, but how far did I go? So let's So what I want is actually the average of m, little m. Remember, n is just the number of steps that I took to the right. M is the number of steps that I took total. So the average m is the total distance that I've gone. That's the quantity that I actually care about. This one is easy to compute. This one is the one I care about. This is just going to be, so from up here, 2n equals big N plus m, or yeah, m equals 2 little n minus big N. So I just stick that in here, and I'm left with the average of m is equal to 2n minus big N, which we sorted out what n is. Oh, man. Covered it up. The average of n is just n times p. So this is 2 times n times p minus n, or let's see, p plus q equals 1 is equal to n times p minus q. So the net difference is the number of steps times the difference in the probabilities of the rates of going to the left or going to the right. So this is equal to the number n times p minus q. We'll need this in a second. So if the probability of going to the left and the probability of going to the right are the same, then what is m? 0. So, and the next bit, the average distance squared, the average square distance that you've gone. Really what we care about, the average square distance you've gone is just equal to, we just plug the same thing in. You get 4 times the average of n squared minus 4 average n big N plus big N squared. I just square the thing that I stuck in here. And then what I really care about is the variance, which is m squared minus little m squared. So again, the square's on the inside here and the square's on the outside here. So make sure you're keeping that difference. You do a little bit of algebra, and you're left with 4 times big N times P times Q. So now, all right. So I've been talking about discrete jumps. So let's see. M squared equals 4 yeah. So if P and Q are, if we have a balanced process, so the probability of going to the left is the same as the probability of going to the right, then P and Q are both half. And the average distance that you've gone, m squared, is equal to the number of steps. So the RMS displacement is the square root of the average m squared, which is the square root of n. This is a result that will show up a buttload of times in a bunch of different places. When you've got a random process like this, the variance goes like the square root of n. Because, or the RMS, the standard deviation, goes like this, goes like the square root of n. So this shows up when you have any kind of noisy process, or many kinds of noisy processes. Not every noise is like this, but most noises are like this. The amount of garbage that you get goes like the square root of the number of steps that you get. So m RMS equals the square root of big N. Okay, so now this is all kind of weird. So let's first, first molecules don't make individual steps. It's a continuous process. And second, we want to turn this into physics units. So, I don't need this. Okay, so the first thing we need to do is turn this into a continuum. So this binomial distribution is hard to deal with because I don't know how many steps the oxygen molecules in my box of air have taken. It's on the order of, I don't know, 10 to the 40, a lot. Like how small is the quanta of space? So let's make this a continuous function first. So have you guys seen Stirling's approximation anywhere? Anybody? No? You? Okay, so Stirling's approximation, you will see this when you get to StatMech. So this is called Stirling's approximation. N factorial is equal to n plus 1/2 log n minus n plus 1/2 log pi 2 pi plus things that are order of 1 over n. Sorry. This is the log of n factorial.
It's root 2 pi n times n over e to the n.
What?
Stirling's approximation.
Where?
It's just root 2 pi n times n over e to the n. And then times n over e to the n. To the n power on the, yeah.
Equals what?
Equals approximately n factorial.
Sure, I'm going to use this one.
But
Yeah, all right, so that's the same thing.
Yeah. But that's the natural log.
I want the natural log. That's where I'm going. So yes, so this is Stirling's approximation. If you take the log of it and expand everything out, we'll do that. So we can sort out that the log of P of M and N is equal to, here's a page of algebra that I'm skipping. So you take this. I didn't actually write it down. Let me read it. So we take this, we take its log, we plug it into here. You could probably do it a little bit more directly if you don't take the log first, but I don't know, this is the way that I went up the mountain. You're left with minus 1/2 log of 2 pi NPQ plus P minus Q over sigma n squared delta m minus 1 over sigma n squared to delta m squared, where we're introducing two variables. Sigma m is just 4 pi NPQ. That's just the variance that we found before. And delta m is m minus the average of m. So basically, Stirling's approximation is this. You drop it in here, and you're left with P of and big N is equal to, can you see it from here? I don't think so. 1 over 2 pi sigma m squared. Square root of that, the square root is, this square is inside the square root, e to the 1/2 delta m squared over sigma m squared. Now we have Gaussian. Yeah.
What does this say?
What does this say? That's a good question. So what is this expression telling us? This is telling us the probability that we've gone a distance of, I can rewrite this as delta m. The probability that I've gone a distance delta m given n steps is equal to e to the, oh, there's a minus sign missing there, e to the minus delta m squared. And then some other stuff to make it all add up to 1. So, I'm going to turn this into a diffusion equation in a second. But so what does this mean? Let's call this P of delta n big M. This is equal to 1 over, okay, this constant out front is just to make it sum to 1. So 1 over 2 pi sigma m squared, square root of this. E to the minus 1/2 delta m squared over sigma m squared. So this says that now I'm measuring delta m. This is how far away I've gone from where I started. It's just like m that I was looking at over there, but now I'm just taking off the mean. So delta m is going to look like, okay, this is just a constant to make sure that it integrates to 1. The important bit is e to the minus sigma squared. So when delta m is 0, or sorry, delta m squared, when delta m is 0, then I'm left with 1, or whatever this constant is. And then as I increase delta m in either direction, it falls off like yon. So the probability to have gone this far is this much. This is a classic bell-shaped curve. And this has a width. The width of this is roughly sigma m.
Where do you measure the width from?
At a half. So I'm going to put air quotes on there, and I'm going to put air quotes on the point that I draw that. There is a point where you can draw that where the distance from here to here is sigma m. And that is equal to, I plug in sigma n up here, this turns into e to the minus 1/2. Right? So it's e to the minus 1/2 times the normalization constant, and that's the height at which. So now that's really just e to the minus 1/2. So you're just down by a factor of about square root of 2. So this is the probability that you've gone a certain distance, delta m. This is a Gaussian. We love Gaussians. Why do we love Gaussians? Because you can integrate them all day. You can integrate them 1 million times by hand. You can differentiate them 1 million times by hand. They have all these nice integral properties. The integral of this thing is 1. The integral of x times this thing is something you can write down. Because the last thing we want to do is we want to turn this in. This is now m and n. Let's turn this into x, an actual position. So this is going to be little n times delta x. Now we're walking by certain step sizes. And some time t, which is going to be big N times delta x. T is big N times delta t. Oh, I'm sorry. That should be m times delta x. And that should be big N times delta t. So if we define a constant d, which is just equal to 2pq delta x squared over delta t, this is just to make the units work right, then my probability of x and t is just going to be equal to 1 over 2 pi sigma m squared, square root of that e to the minus 1 x minus average x squared over d times time. Okay, so the probability distribution of a quantity is going to go like this. So what does this tell us? So this says that if I have a diffusive process, now I haven't shown you yet, but this is also the solution to a process like this. So if a process that has a time derivative of some quantity equals some constant d times the second spatial gradient of the quantity, one solution is a Gaussian. So let's say I start with a delta function. So I just start with all of my heat in one point. It's going to expand like a Gaussian, and the width of that Gaussian is going to go up with time. It's going to spread out. Does that make sense? So if I look at how this works in time, if say this is the heat equation, and I dump a bunch of heat into one zone, so I just set one thing on fire, and I let the heat spread out, it's just going to be another Gaussian, but the width of that Gaussian is going to expand with time. So it just goes narrower, so it just gets wider and wider and wider, and it just spreads out like a Gaussian. So like a series of Gaussians. So, okay, diffusion. Let me sum up everything I just said about diffusion and all the important takeaway points about diffusion. And where am I? Okay. Okay, so so if I have a random walk where I have some probability of P going to the right and Q going to the left, then the average distance that you've gone is going to be the number of steps times P minus Q. The RMS displacement is going to be 4 times n PQ. So if P equals Q, then this is equal to 0, and this is equal to no, sorry, the 4 cancels. Just n. 2, random walk processes also give us a diffusion process, or Gaussians. P of x and t is equal to 1 over 2 pi sigma squared e to the minus 1/2 x squared over d times t. Not t squared, just t. So then also, you can work out what the variance does as a function of time. Average x squared is just going to be, oh no, I'm missing a number. Don't write that down, sorry. Okay, so why am I going through all this? Because I've got all these squared terms. So let's make a contact to this. So now I'm going to show you why this is relevant. Because that's the operator that we see a lot. That's the operator that we're gonna that is gonna show up. So random walks smear things out, make Gaussians, spread the Gaussians out. Further, no, I'll talk about that in a second. Okay, so now we want to make contact with. Do I have another board here? No, I don't. Leave that up. Use this one. So, what physics operator do we want to use? So, if I've gotten to a point P, let's say I've gotten to a point wherever I am. My starting point was way over there. I've been random walking around this field for hours and hours and hours. What's the probability that I got to this point? Well, the probability that I got to the probability that I'm here is P of m of an n. Let's call this one n plus 1 just for nomenclature. N plus 1, it came from, so this is n plus 1, this is n, it came from somewhere. It could either, so if I'm at this point, I either, in previous, so time is going down this way, right? If I'm at this point, I either started to the left and went to the right, or I started from the right and I went to the left, right? So the probability that I'm here is just going to be, so the probability of moving this way is P. The probability of moving this way is Q. The probability of being here is P of m minus 1, n minus 1. And the probability of being here is P of m plus 1. And, oh, sorry, we're not calling that n minus 1, we're calling that n. This one is n plus 1. That's really, like, I could call this n and this n minus 1 and everything works out just fine. Doesn't matter. Does everybody follow this here so far? So the probability of being here is the probability of being here times the probability of jumping plus the probability of being here times the probability of jumping. So this is P of big P of m minus 1 and n plus q of big P of m plus 1 and n. Okay, so now I'm going to do two things. I'm going to subtract P of m and n. That's the probability of being here in the middle. Doesn't really make a ton of difference for us right now. So I'm going to subtract P of m and n from both sides, this side and this side. I'm going to divide through by delta t, and I'm going to multiply by a couple delta x over delta x. So the right-hand side turns into P of m n plus 1 minus P of m n over delta t. And the right-hand side turns into P of P times, and a handy thing is P plus Q is 1. So I'm going to subtract this. I'm going to split it amongst my two terms. I've got a P term and a Q term. I'm going to split it amongst those terms. So I've got P times big P of m minus 1 n minus big P of m n plus Q of big P of m plus 1 n minus P of n n. And we've got both of those over delta t. We'll have a delta x, actually both of those over delta x. And we'll put a delta x, delta t out front. This small chart is really cramping my style. Let's write that again. And I'm gonna shorten my notation. So P of m n is P of I j. No, I'm sorry. I hate that notation. I'll use the notation that I actually like. P of m n is P of I as a subscript, n as a superscript. Why do I want to write it like that? Because it's compactor, and that's it. Only because it's smaller, and I'm going to write something gross in a second, and it's really easy. It's really useful if you have your things compact when you write finite difference equations like this. Okay, so this turns into P I j plus 1 minus P I j over delta t. Equals minus P delta x over delta t times P I j minus P I minus 1 j over delta x plus Q delta x over delta t P of I plus 1 j minus P of I j over delta x. So one thing that you need to always keep in mind is what the definition of a derivative is. Because so f prime of x is f of x plus delta x minus f of x over delta x. Everybody loves this, right? So this is a derivative in x, and this is a derivative in x, but let's draw a couple points. Okay, so these are my points in space. Here's I. So this term is this box minus this box. And this term is this box minus this box. So I'm taking this difference and I'm subtracting this difference. That is the second derivative. Does that make sense? So this whole thing on the right-hand side is the difference of differences. And it becomes the second derivative. So this turns into dp dt, because I'm taking this time derivative, equals some number times d squared p dx squared. And that number is upstairs on my desk. It's 4p cubed delta x squared over delta t. I'll put that in quotes just in case there's something that I forgot. But okay, so how did we get here? What did we do? So we said to get here, I can either come from here or I can come from here. Yeah, and then we did a math stuff. I'm not as, this proof leaves me I don't know, unsatisfied. I see where the math comes from. You can see where the math comes from. So this is a derivative, this is a second derivative. Now we're at the second derivative term. I don't feel like I have all of the love that I want from this proof. But the important bit, well, let's add this to our list of primary takeaways. So this kind of quantity is diffusion. It spreads things out. It's well characterized. It has the mean squared goes like the time. So when we go through the same stunts that we went through before, if I try to get mean x squared, this is going to go like the time because of all the things that we did already. Before we had mean x squared going like the number of steps, but that's just going to be equal to the time. So this we'll come back to, because in the book he showed a turbulent diffusion when the inertial range is smaller than the scale of interest. So the turbulent diffusion that he talked about in the book is only for a particular scenario, which I'll talk about in great depth on Thursday. That is all I have to say about diffusion right now. There will be some homework problems on this, so anything that you're confused about now, you will continue to be confused about it in homework, and then you will be not confused, and then we will learn. Does anybody have any questions about anything? Good so far? It'll become more clear once we do something with it. So, thanks a lot.